Yeah, hi all, good morning. So, I've pasted the link in the chat box. Please join soon. We'll start the quiz soon. People in the session, please join the quiz so we can start and wind it up soon so your session can be continued. 1 more minute. Whoever wants to join, please join. Then I'll start the quiz. Okay, so I'll start the quiz. First question: which activation function is typically used in the output layer for multi-class classification purposes? Second question: what is the main purpose of the back propagation algorithm in neural networks? Question: which of the following techniques is typically used in conjunction with back propagation to optimize the weights? Fourth, what problem does the back propagation algorithm aim to solve? What is a computational graph in the context of deep learning? In a computational graph, what do the nodes typically represent? What do the edges in a computational graph represent? During back propagation, how does the error propagate through the computational graph? What is the output of the back propagation process? Last question. In which part of the computational graph is the loss function typically located? Great. So we are done with the quiz. Vipul, you can take over. Thank you, everyone.
Yes, hi everyone. Good morning. Yes, so what was the last part that we have discussed? Yes, everyone. Mm. What did we study in the last session? Okay, we have performed this hyperparameter tuning in decision tree, right? And we also have discussed the difference between random search CV and your greed search CV, right? We also have discussed this. All right. So in this session, we are going to discuss random forest, another machine learning model. All right. So in this session, you learn about random forest, one of the most popular algorithms in machine learning. Random forests use a technique known as bagging, which is an ensemble method. We'll see that what is bagging. So before you learn random forest, let's first understand the ensemble or ensemble. What do you mean by this? Ensemble learning. What is ensemble learning? Right? So it refers to a group of things which is viewed as a whole rather than individually. In an ensemble, it is known as collection of models. And collection of model is used to make predictions. Simple. So instead of using only one model, we use collection of models to make predictions rather than individual models. Individual models, right? Arguably, the most popular in the family of ensemble is or ensemble models is the random forest. Is the random forest, right? So which is an ensemble made by the combination of a large number of decision trees. So what is random forest? Ideally, your this word will uh, tell you the story about the random forest. What is random? What do you mean by forest? It's a collection of trees, right? Collection of trees. But here we are dealing with machine learning, so it is collection of decision trees. Simple. Forest is nothing but it's a collection of trees. But here we are dealing with the machine learning. So combination of a large number of decision trees, right? Combination of a large number of decision trees, right? So in principle, ensembles can be made by combining all type of models. An ensemble can have a logistic regression, a neural network, and a few decision trees working in unison. So it's not like you only have combination of all the decision trees. It's not like that. Random forest, or basically, random forest is a collection of decision trees. That is correct. But ensemble means we are using collections of models. So ensemble or in ensemble, we can have collection of models like logistic regression can be there, your neural network will be there, right? Then a few decision trees are could be there. So it can be anything, not necessarily that it should have any decision trees, right? But random forest, we have all the decision trees out there. Now, before you understand how ensemble works, the following question may arise in your mind. How does a collection of models work better than individual model? First question. How does a collection work better than an individual model, right? Second could be, how do you choose individual models to form an ensemble such that it is better than any of the individual models? How do you choose the individual models to form an ensemble such that it is better than any individual models, right? We'll see that. So these are the two questions. We'll be having answers to this now. Question number one, question number two. So we have a concept of diversity and acceptability. Nothing special. Diversity and acceptability. So what do you mean by this? Is nothing but here, right? So ensemble models are somewhat analogous to team of individual players. Just consider a scenario. It's just like your team of individual players. So suppose if you were to choose a football team, right? Hmm. What you'll do? You would take the following two steps. Yes or no? You'll choose people with different skill sets, such as defenders or attackers, and a goalkeeper to ensure diversity, right? Then you'll choose good players. That is also another thing. That is to ensure that all players are acceptable. Let's consider a scenario. Let's say you are preparing for FIFA World Cup 2026 and you are being head coach of Argentina, let's say, right? So what you'll do, you will choose player with different skill sets such as defenders, attackers, and goalkeeper to ensure diversity. Yes or no? Or will you go with only attackers? That will not be the case, certainly. Second, you choose good players to ensure that all players are acceptable. Acceptable means you should be having good quality players, not necessary that I mean, it's not acceptable that you choose only the players which you are familiar with, right? It's not like that. Then, from the point of view of their skill set, from the point of view of their skill sets, they should be acceptable, right? And at least better than a regular person, better than a regular person. So diversity ensures that models serve complementary purpose, which means that individual models make predictions independent of each other. What is diversity? Why we are choosing different people with different skill set, guys? Because let's say this is your field, football field. Let's say this is your football, right? Um, we have this thing. We have this. This is D and this is net, right? So the reason why we are choosing people with different skill set, defenders, attackers, goalkeepers, because whenever there's a time, let's say whenever you want to attack and whenever you want to score goal, these three people will do your task, right? Whenever you want to um, create a play, so these are known as playmakers, midfielders, and then you have defender, right? So 4-3-7 and 4, let's say. Sorry, not 4. You can have 3 only, and one will be your part of goalkeeper. This here he will be, right? So 4-3-3 or 3-4-4. 3-4-3 is your combination. So these people will do their task to defend opponent team from scoring a goal, right? These people will, what they will do, they'll just create a game so that they will help defenders as well as attackers whenever it is required, and attackers will score the goal whenever attack opponents whenever it is required. Yes or no? So having said that, this thing, diversity, what it does is it ensures that the models serve complementary purposes, which means that the individual models make predictions independent of each other. Yes or no? For example, a random forest is an ensemble with a large number of trees as individual models. And diversity, what it does is, diversity, it ensures that even if some trees overfit the other trees in the ensemble, will neutralize the effect, right? And the independence among the trees results in a lower variance, lower variance of the ensemble compared to a single tree, right? The reason why we are going with the team, because we want to eliminate the effect of, uh, let's say, if particular player, let's consider that scenario only. Let's say if this player, this particular player, this attacker, we call it as right wing, right? Winger. He'll not be having ability to play in the left hand side, right? Will he be able to play on the left hand side? Certainly not. But this ability, this disability of playing on the left hand side is nullified by, neutralized by this player, right? Similarly, this player is not, it's not possible for him to play on the right hand side here for this player, right? He cannot play here. So this drawback is satisfied by this player. Yes or no? So the team of individual players will help you out in this scenario. Let's say it ensures that if some trees overfit, your other trees will take care of that, right? And it will be independent of each other. For an example, if you are, let's say, random forest is a collection of tree. What do you mean by that? This will be one tree, let's say. The other tree will not be same like that. It will be totally independent, meaning that you will be having different trees or different splitting on different criteria. For an example, let's take that scenario where we are predicting whether person will have heart disease or not. Here, the case will be, let's say, di cholesterol level. We are splitting on cholesterol level. It should be greater than 230 and something like that. Here we are splitting on age. Then again, we are splitting on different criteria or different condition. So altogether, your trees will be different, right? And it will take care of the scenario which is not, which this tree is not capable to take care of, right? Some disadvantages will be there for this tree. It will take care by this tree, right? Some disadvantage will be there for this tree. It will take care by first tree. So like that, all the effect will be neutralized. So that's the reason of diversity. Right? So that's your theoretical part of diversity. And acceptability means, simply means acceptability simply means you guys will be, let's say, the model should be acceptable first, first of all, right? It should not be like you're creating a dysentery model, let's say a classifier model, and the accuracy that you're getting is very less, 0.4, right? It should not be the case. We should accept good players in order to win this World Cup, right? We should choose good players to ensure all players are acceptable. Similarly, we should select a model that should be better than at least better than random model. And this is pretty lenient criterion for each model to be accepted in, excuse me guys, this is pretty lenient criteria for each model to be accepted, into the ensemble, right? That is, it has to be at least better than a random guesser. It has to be at least better than a random guesser, right? It has to be at least better than random guesser. Random guesser, what do you mean by random guesser? It's just like this. Suppose you are tossing a coin. Again, this is something which will come across multiple times from now onwards. So remember, what is random guesser? The probability of that model should be at least greater than 0.5. So it is possible that it is allowed that you can have 0.51, 0.52 accuracy or probability of having conversion or 0.5t, 52, 53, something like that, right? So just like for an example, you want a model, you want to choose good players, so it should be acceptable. They should be good. So here also, you are creating a decision tree that should be able to classify your person as having disease or not, having disease or not. The accuracy should be greater than, at least greater than 0.5, right? Somewhat greater than 0.5 is acceptable. Let's say 0.6, 0.51, 0.52 accuracy or probability of converting uh, your classes into disease or not disease, at least greater than 0.5, right? At least greater than 0.5. So that is your another scenario of random guess, right? Now, is it clear, guys? These 2 points, everyone? Do you have any questions in this, everyone? Come on, please respond, everyone. Anybody
Can
have any questions in this?
you explain me this diversity once more?
Yeah,
Can you explain me this diversity once more?
diversity. Okay, it's very simple, right? What is different in what is difficult in this? Diversity means we should have uh, we are choosing people with different skill set, such as defenders, attackers, and goalkeepers. That is diversity for you for this particular problem statement. In random forest, diversity means this uh, model that you are selecting should be independent of each other. Independent of each other means, suppose in decision tree, what we have discussed, we are creating only one decision tree, right? Suppose this is your decision tree. We are creating this thing, this one, this one, this one, and this only will be a final prediction. Yes or no? Suppose uh, you are dealing with the decision tree which we have discussed over here. Let's say this decision tree, or we are selecting the disease wala scene where we have created a decision tree. Where is that? Actually, not here, right? 29th December. Yes, this one, right? Or let's take this. So you're taking only one model to make prediction, right? What about the drawback of this model? This model is overfitting. We have discussed that. Decision tree is always an overfitting model. It means that your training accuracy will be high, but testing accuracy will be poor. It fails to generalize well on your test subset or test data. Yes or no? So what do you mean by this? We cannot simply use one model. The reason is we are not getting good accuracy. So idea here is to combine all the models out there, or not all the models, different decision trees, where this time I'll be using another criteria where age equals to greater than 50, right? Do you agree with this, that if I select this age greater than 50, I will be having different decision tree than this? Yes or no? So my decision tree will be different in what sense? I'll be able to capture another pattern, another data, another thing, another accuracy, which this decision tree has not captured if I select this thing. Yes or no, Gopi?
Yes, sir. Yes.
Right? Then again I'll be selecting another thing, let's say age equals to greater than 40. And I'll be having another decision tree which which will observe another pattern, another uh, trend, which these two decision trees are not captured, right? And then we make a combination, or like we make a aggregate of this all the decision trees into the picture. For example, this decision tree is giving me 0.68 accuracy, right? This decision tree is giving 0.75, and this is 0. Let's say 8 or 0.7. So we'll take an average of this average for the final prediction, right? And that is how you solve the problem of overfitting. That we can see it after some time, right? But the idea here is to have a diversified portfolio. You might have heard this fact, diversified portfolio, if you guys are um, you know into investing, right? What do you mean by this? You simply not only take stocks related to any one segment, let's say pharmaceutical segment, right? The idea here is you can go with the finance or fintech, you can go with the manufacturing organizations, you can go with the banks. So idea here is, suppose if there is some critical condition wherein your pharmaceutical industries are not performing well, your stock will be dropping, right? But then at that particular time, suppose this is also dropping, let's say this is also dropping, but banks are into all-time high, right? And why we are going with the diversified portfolio? In order to nullify, minimize your losses, right? Then there will be another scenario where pharmaceutical industries are performing really great in what times? Let's say COVID times, right? COVID times, all the sectors were all-time low, but pharmaceutical sector were all-time high, right? Fintech, they were also performing well, but very low and very poor, for an example. So the idea here is to have a diversified portfolio to, just uh, to reduce the task of to reduce the chance of your losses, right? So that is how your diversified or diversity is. I hope this is clear now. We'll go to the next part. Now you'll be asking this question, ki how you achieve the diversity, right? So there are a number of ways in which you can bring diversity. For an example, let's say, for an example, um, just a minute. Right. For example, first point, we use a different subset. I already have discussed this, and you guys are already well familiar with this point of training data, subsets of training data. For an example, let's say you have this data with you, right? You have this data with you. This is your data point. These are your data points. Right? We have 15 data points. So what you're doing is you're selecting different subset of data for different decision trees. Like I'll create one decision tree in which I'll be having only yellow data points, let's say 1, 2, 3, 4, 5. Right? That is my decision tree number 1. Right? It will give me some output. I'll be creating another decision tree in which I'll be having this data points. Then I'll be creating another decision tree in which I'll be having this data points. So it's a different subset of data, and that brings your diversity. Yes or no? Like you will be having a decision tree, different decision trees in which you will be having different data, right? Yes or no, guys? Another decision tree you'll be having in which you'll be having this data. So different subset of training data, right? As you're providing different subsets of training data, the accuracies of all these three decision trees will be different. Yes or no? 70, 80, 90. And then you'll combine the these three outputs and make a prediction, right? That is your different training subset. Second example could be, we use a different training hyperparameters. And this is also very easy. You guys are already familiar with hyperparameters. How do you choose hyperparameters? You go to official documentation of random forest, and you guys will be having a look at or selecting these parameters. So suppose for one decision tree, I'm only selecting n estimators, criterion, and max depth, and I'm building a model. For another decision tree, I'm taking minimum sample split, minimum sample leaf, and minimum weight fraction leaf. Again, I'm selecting third decision tree in which I'll add max features, maximum leaf node, and minimum impurity decrease. So likewise, you can bring the diversity in your portfolio or in your this is a random forest. Then we use different uh, types of classifiers. Just like the case you are using logistic regression classifier and build a model. You'll use not random forest, KNN classifier. You'll use this time decision tree classifier. And you'll combine the result of all these three models, right? So there might be chance that your logistic classifier are not capturing a good result. Your KNN will capture good result, right? There might be chance that there are some drawbacks of all the models out there. So one drawback will take care of by the another model. The second drawback will be taken care by another model. Yes or no? So likewise, you can use different types of classifiers, different models, and we use a different features. This is also something which we have discussed. Like you are building a decision tree on age criterion, age feature. Now this time I'm going to create a decision tree in which I'll be taking cholesterol level, right? Then again, I'll take a decision tree. I don't want cholesterol. I don't want age. I'll select BP as the criteria, which is my first um, root node, right? Creating a decision tree. This time BP as the criteria. BP is greater than 250 or not 250. 250 can be there, yeah. Or anything for the matter of fact, right? So likewise, you can create different features, use different features to achieve the diversity. Not a big deal, right? So that is how your uh, problem of underfitting, overfitting usually gets resolved, right? Now that you have understood different ways to bring the diversity, but what makes an ensemble better than individual model? We have not discussed that. You'll be having a question: what makes uh, what makes an ensemble better than individual model? We already have discussed this thing. Like anyway, just consider a scenario where you are not maintaining diversity. You are only selecting attackers. That is not good. Or you are selecting poor players. That is also not good. So diversity, I mean, your ensemble brings diversity and acceptability. That is how your performance of the model, accuracy of the model, R2 score of the model increases. Simple, right? So that is how we um, what makes an ensemble better than an individual model. That's make that is what ensemble that is what makes ensemble better than individual model, right? Right. Perfect. So I'll give you 5 minutes, just 5 minutes, not more than that. You guys go through this whatever we have discussed till now, and then we'll be dealing with the um, one scenario. Just a minute. Just a minute. Give me a minute. We'll be dealing with one scenario where we'll see actually how uh, your ensemble improves the overall performance of the model, right? Very simple case, very simple case. An example, a comprehension basically, right? So it's 9:43. Go through this thing, guys. Take your time just for your revision, and we'll be starting exactly somewhere around 9:50 a.m. கேக்குதா? ஹலோ. All right. So let us see one comprehension. Let's say you are building a model, right? What is that model is all about? So first of all, let's take this question that how can you guarantee that if the two conditions of diversity and acceptability are fulfilled? How can you guarantee? How can you guarantee that if the two conditions of diversity and acceptability are fulfilled to make it an ensemble, to make an ensemble, right? It will be better than individual model or not. How can you guarantee this? So let's see this. Suppose um, you are creating a model. Let's say this is your models that you are using, M1, M2, M3. And these are the predictions. Yes, no, yes. And your majority score will be this time. So three models are there. First model says prediction as yes. Second model is no. Final model says yes. So what will be a majority? Is it majority prediction? What will be that? It will be yes or no. Everyone, what's your majority score or majority of the prediction? It goes for yes, right? It goes for yes. Simply. So your acceptable model, first point, should be, let's consider another scenario. You're tossing a coin, a single coin, right? So here, your probability of head becomes probability of tail, right? And that is 0.5. And what we said is, what we have discussed a criteria that your model is acceptable. Consider that it should have prediction greater than 5 or at least 5. At least 0.5, that is half accuracy. So this can be your acceptable model, right? This can be your acceptable model. So now third case, like how your model improves the accuracy, right? How your ensemble improves the overall performance of the model. So what do we have is we have three models again. These are the cases. These are the results of each model, right? And one, two, it's going to be 1, 2, 3. Yes. And here it is result of the ensemble. Result of the ensemble. And here we have probability. Probability. Okay. So case number 1. Here you have M1, M2, and M3. The result of the ensemble would be 1 correct, correct, correct. Suppose 3 model says yes, yes, yes. Your result will be correct only because majority of the vote goes for correct. And this time your probability is, let us say, just consider a scenario where you are dealing with the problem that you are basically you're classifying a scenario where your So basically probability of being correct is given to us. Probability of being correct given to us, that is 0.7. Just consider hypothetical scenario, or the um, just consider that you are building a model and it is already being given that probability of being correct, that your model is correctly predicting whether person has disease or not. Disease or not, correct probability is 0.7. So what will be your incorrect probability? It is 0. Yes, guys. Sum of probability is always sum of probability is always. I'm asking fifth standard, fifth level question. Sum of probability is always. I'm asking sum, Gopi, not range. I'm asking sum. Sum of probabilities is always. We have 21 students and only 2 students are answering this question. What's the probability of sum? Sum of probability. It's always 1, right? So here, if probability of correct is 0.7, so what will be a probability of incorrect? 0.3, right? So let us write down incorrect as 0.3. An ensemble result will be probability of correct. Let us write down that 0.7 into 0.7 into 0.7 for this model, because we have 3 correct, right? Second case now. All possible cases we are just taking out correct. This time this is correct and this is incorrect. Third possible case is correct, incorrect, and correct. Right. Fourth is incorrect, correct, correct. Fifth is incorrect, incorrect, correct. Sixth is incorrect, correct, incorrect. Then seventh, correct, incorrect, incorrect. Then eighth is incorrect, incorrect, incorrect. Right? Only 8 possible cases will be there, right? If you want, you can try this out. Apart from this, you will not be having any other possible scenario. So at this is correct, correct, majority goes for correct, right? This is correct, correct, 2 correct, majority go for correct. Then here also majority goes for correct. Here also majority goes for correct. Here majority goes for incorrect. Majority goes for incorrect. Here also majority goes for incorrect. And here also majority goes for incorrect. Right? The output basically, because we are taking majority of the votes to finalize the output, final output. Right? So let's make a table. Let us make a table like this. And let's calculate this. Now here it will be 0.7 into 0.7 into 0.3, right? Same 0.7 into 0.3 into 0.7. Third will be 0.3 into 0.7 into 0.7. Then you have 0.3 into 0.3 into 0.7, right? Then this is incorrect, right? Incorrect is 0.3. into 0.7 into 0.3. Here 0.7 into 0.3 into 0.3. Here it will be 0.3 into 0.3 into 0.3, right? So let us write down the values for that. You do this, it will be 0.7 times 0.7 times 0.7, 0.343. This is 0.3 times 0.3 times 0.3 will be this. And this will be uh, 0.7 into 0.7 into 0.3 will be 0.147. It will be same, and here it will be 0.3 into 0.7 into 0.3, 0.063. Oh, sorry, for this also it is 0.63. So that's what your output will be. Now in this table, there are 4 cases each where the decision of the final model is either correct or incorrect. Let's assume that probability of the ensemble being correct is P and the probability of ensemble being incorrect is Q. So for all the data in the table, P and Q can be calculated as for all the data, right? For all the data, it will be 0.343 plus 0.147 plus 0.147. Like, just consider this. What I'm saying is, consider if the output is correct, if the final output is correct, we have P, P, P. And if the final output is incorrect, we have Q, 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 right? Now, for all the correct out there, for all the correct out there, this one, for all the correct out there, the probability of P that is correct is going to be addition of this, right? 0.343, 0.343 plus 0.147 plus 0.147 plus 0.147. So it is 0.784. Now probability of Q is going to be is equals to this plus this plus this plus this 0.216. Right? Now notice how the ensemble has a higher probability of being correct and the lower probability of being incorrect. Right? I have not done anything. I am not saying anything by my own. P is your probability of ensemble being correct, and Q is being probability of ensemble being incorrect, right? Now can you notice this thing that how ensemble has probability, or has a higher probability, for a matter of fact, has a higher probability of being incorrect than any of the individual model. Yes or no? Being correct is 0.784 here, and earlier being correct was 0.7. So can I say 0.784 is greater than my 0.7? Because earlier, what was the probability of being correct? That was 0.7, right? And another case is 0.216 is the probability of ensemble being incorrect. That is less than your probability of incorrect for the original class. So again, if you just take a simple model, a single model, a single decision tree, your probability of being correct and incorrect is very less, right? On the other hand, ensemble will help you out to enhance your probability of correct and decrease your probability of incorrect. So that's how the difference in probabilities will increase and increasing number of with increasing number of models. If you increase again, if you do this scenario for let's say um, in this way, I'll write down over here in this way, you can also calculate the probabilities of the ensemble being correct and incorrect with how many samples? N number of samples, rather 1,000 or 1 million individual samples or models, right? The difference in probability will increase. It will increase if you increase number of models. It will increase if you increase the number of models out there. Simple, right? And improving the overall performance of the ensemble. And that's how the overall performance of the ensemble increases. Now, is this thing clear, guys? Do you have any questions in this? This summarizes your entire ensemble learning. Do you guys have any questions now? Yes, guys.
Oh,
Now, some extra thing I would like to add. Anyway, this is not something which is there in your syllabus, and you'll not find it in your any syllabus out there. This is something extra, just like your if you are going for the master's degree or any higher degree, you'll be finding that we have some other popular ensemble as well. Now that you have good understanding of what ensemble models are, let's look at some popular approaches to ensemble models such as voting, stacking, blending, right? Nowhere we use this thing in the machine learning, boosting and bagging. So we only use this two. That's all. We will not be using voting, stacking, blending. So what does voting does is voting just combines the output of different algorithms by taking a vote. In the case of classification model, majority of the classifier predict a particular class, then the output will be of the majority class. In the case of regression problem, we take average, right? Then another approach is manual ensembling. That is also something which we can see. Then we have boosting, very good approach, and we have bagging, that is your random forest, right? Now we will restrict our discussion for bagging only. We are not dealing with boosting now in today's session because our entire session is focused on random forest, right? In the next session or the next part for the discussion is going to be boosting anyway, right? So that we'll discuss that at that particular time by taking out an example. Again, very simple thing. So I would like to give you guys another example of random forest. Yeah, this is what we are talking about. Oh, this one. Oh, it's so good. So let me take this and let me paste it over here. So as I told, boosting is something which we are going to see later. Bagging is something which we are going to discuss now because we are discussing random forest, right? Now, bagging. What is bagging? It is a combination of two word, bootstrap plus aggregation. Bootstrap plus aggregation. So B is for from bootstrap and AGG is from aggregation. So that's how bag or bagging comes into the picture, right? B from bootstrap, A from AGG. So that is how bagging is coming into the picture. Now, what is bootstrapping? Bootstrapping means just allow me to open this presentation. Yeah, perfect. We have here. Okay. So what is bootstrap aggregation? See, bootstrap means you take a random sample from the entire data. That is bootstrap sample. That is one concept in statistics. Bootstrap sample means random sample from your entire data. Let's say this is your entire data. Let us consider this is your entire data, right? A, a basket full of fruits, different kinds of fruits. So we have taken bootstrap sample, BS, BS1, BS2, and BS3. So for example, you have selected some portion of this basket and added this to, created a decision tree from that. Here also, now what we do is interesting fact is, first of all, we take a sample, we create a decision tree, then again we'll replace this sample to the into your original data set or original basket. So creating a sample, replacing it, creating sample, replacing it, creating sample, replacing it. So it's not like here we are using a sample, then remaining part, uh, from the remaining part itself we are creating another sample. It's not like that, right? It's not like that. So that is how your bootstrap sample is. Bagging chooses a random sample from the entire data, that is bootstrap sample. We create each model by different bootstrapping with replacement. Row sampling with replacement is known as bootstrap. That is what I have discussed. What is row sampling with replacement? And the step that the step yeah, the step which involves combination, combining all the results and generating output based on majority of the voting. Step which involves combining all the results and generating output based on majority voting is known as aggregation. A step which involves combining all the results and generating the output based on majority of the voting. So what we have done is we have created a recent tree model, recent tree model 2, recent tree model 3. This model is giving me output as class A. This is giving me output as class A again. That is apple, right? And this model is giving me an output as banana, right? Final output, just like correct and incorrect that we have discussed just now, right? So here we have different classes. We have multiple classes like class A, class B, class C, class E, something like that. A for apple, B for banana, right? And there might be pineapple and some kind of fruits. But this decision tree is giving me an output as apple. This is also giving me an output as apple. This is giving me an output as banana. And I'm going to take majority of the votes. I'm going to take majority of the votes because this is an ensemble. This is an method. This is your bagging, right? Aggregation. What do you mean by aggregation? What is aggregation? This is bootstrap, taking a sample with replacement bootstrap. And what is aggregation? So aggregation means, let's say, um you're preparing, let's say there is one, what we can say, campus um, interview. Let's say you are at in the final year of engineering, and we used to have campus interview, right? Let's say TCS, Infosys, they used to come in your campus and they used to recruit, they used to hire candidates who are there in their final year of engineering, right? So what they used to ask is they used to ask aggregate marks. Do you remember this? Aggregate marks or aggregate percentage. So what is that? Aggregate first year, second year, third year, and last year. Till now, let's say you are only in your eighth semester. So first year, first same, first year, second same. Similarly, second year, first same, second year, second same, third year, first same, third year, second same. And you're in the last same, that is your eighth same now. So we don't have a result out there. We are still in the last semester itself, but we are appearing for this exam, for this interview. So you're, let's say you have scored 75% in first year, 70% in second year, 60% in second year first same, 65 in your second year second same, 17 again in your third year first same, 75 in your last. third year last same, and 75 in your fourth year, uh, first sem, right? And what is your aggregate percentage now? So for that, what we do is we take a mean. We take a mean of all this percentage out there. It is going to be this one plus 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 this, and this entire thing divided by 7, right? 1, 2, 3, 4, 5, 6, 7. So instead of that, we take an average, right? We can take an average. Average of what? Average of this thing. That is 70. It is coming out 70. Yes or no? So you say that you used to write down in that form, your aggregate marks is 70. Similarly, your average of this thing is, what is your majority classifier? Majority of the votes. Majority of the voting goes for apple. So your final output is going to be apple, right? So you're predicting your fruits. Let's say predicting fruits from the basket. You are using different decision trees, random forest approach, and your final output is based on the majority of the voting. That is your apple. That is your apple, right? So this summarizes your entire random forest model, right? So this can be another example, or another figure you can consider. So there can be n number of figures, but I hope you guys got an idea about how random forest works. Very simple. Nothing difficult in that, right? Again, this can be another example. You're predicting an expression of different people, making a classifier out of that, and majority of the vote goes for happy. In this case, majority of the vote goes for happy, right? We have two happy, one sad. So majority of the voting is happy. So like that, your random forest can be having uh, uh it will work. It works like that, right? N number of problems you can find it over here. All right. So that's what we have for your random forest. Now what we'll do is, yeah, we will discuss the disadvantages of random forest first, right? It's not the case that it is not having any disadvantage, right? So bagging you have understood. So what are the advantages of bagging? I'll write down over here. Advantages of bagging. What are the advantages of bagging that you have? Perfect. Chalo, let's do that. Let's see. So bagging works well with high variance algorithm, and it is easy to parallelize. We'll see this thing. Sort of fancy, like we are using fancy words, nothing special over here. Parallelize. Just Parallelize, right? By high variance, we mean algorithms which change a lot of slight changes. By high variance means algorithms which change a lot with slight changes in the data, as a result of which this algorithms very easily overfit. We mean that we change a lot with slight changes in the data, as a result of which these algorithms very easily overfit if not controlled. You can take an example of decision tree. If you do not control decision tree, uh, you can recall this, right? Decision trees are very prone to overfitting. Now, if you don't tune parameter, if you don't tune the hyper parameters well, it will overfit 101%. So your bagging will help you out to rescue this problem. Bagging works very well for high variance, high variance model like decision trees. Meaning that even though you are using multiple decision trees, even though you are using multiple decision trees, and as you know that decision trees overfit, but as a combination of this will not be your model will not be overfitting, right? It's very very impressive. Even though you are using combination of decision tree which indefinitely overfits, but here you are using combination of decision trees, so it will not overfit, right? But disadvantages of this particular approach, disadvantages of bagging are are disadvantages of bagging are you cannot really see individual trees one by one, right? Can you see individual tree? You cannot see individual trees one by one, right? And figure out what is going on behind the ensemble, right? It's a combination of n number of trees working together. This will leads to the loss of interpretability, which was an advantage of your decision tree, right? You cannot see individual trees one by one and figure out what is going what is going going on behind the ensemble as it is a combination. It is a combination of n number of trees working together, working together, and this leads to a loss of interpretability, and also does not work well when any of the feature dominate, because of which all decision trees look similar, and hence the property of diversity of ensemble will also lost. We'll see this thing every point out there. Sometimes backing can be computationally expensive. See, we have seen this thing that decision tree is very easy and explainable to your common man, yes or no? Even though if I'm not using any technical term, it is very highly interpretable, right? You have created dysentery, and if you simply give this to any layman out there, he'll be able to understand that what is going behind your model, right? What is going behind your decision tree. But in linear regression, is that the case? Is it not this? It's not the case, right? You have to explain this. Interpretability is very less. Similarly for logistic regression, it's not highly interpretable. But decision tree is excellent interpretable. When it comes to interpretability, it is excellent. But as you're using multiple decision trees, you cannot see what is going behind, right? The second point is, that was your first point. Second point is, sometimes bagging can be computationally expensive, computationally expensive, and is applied depending on the case. is applied depending on the case. Computationally expensive means we are required, there's need of a lot of computations, right? So you have to create decision tree one, your model will solve that. Here you'll require one computation, let's say. Here you'll require computation, second computation. Here will require processing your RAM, right? So it will require separate memory allocation or separate processing in the RAM for this decision tree, for this or for this, right? So it is computationally expensive. There's one highly technical word which is known as computationally expensive part of thing. What do you mean by that? Computationally expensive means whenever you have high features, we say that your model is computationally expensive. What do you mean by this? It means it requires a lot of memory, space, time, and cost as well. Why cost? Because we are in need of high GPUs, high CPUs, high RAM, right? So most of the algorithms, decision trees, or let's say neural network will require, or your normal laptop will not be sufficient to deal with this network or this model, right? You have to purchase GPUs and TPUs as well. So if you just go to Colab, here you'll find that we have these three processing units which are available free. But if you want to access premium GPUs, you have to purchase additional compute units, which will save your time, right? So you can see the cost for Colab Pro. You get faster GPUs, upgrade to more powerful GPUs. Colab Pro Plus, additional 400 compute units for a total of 500 per month. So sometimes you will find that your task is not completing or your model is not able to give you output in 24 hours, right? Sometimes it requires more than 2 days, 3 days, 4 days, right? So at that point, don't imagine working on a real normal computer like this, the one which we are using, right? We will not be using that. We'll purchase the faster GPUs and CPUs, something like that, right? So that's why I told you NVIDIA GPUs, if you see, it's in high demand nowadays. The reason is this one only, right? Okay, so that's what we have. And depending upon the compute units that you're using, your price will vary, right? Anyways, if you are working in the industry, it's not that much difficult for you to purchase. Not for you, for your organization, obviously. $58.99 in rupees is not that costly, right? It's 5,000 rupees per month, I think. Yeah, per month. For individual kind of task, it is 11.79. And that is also not something which is very costly, which comes up somewhere around 1,000 rupees for an individual purpose, right? So you can think on this if you are very serious about the computation and working on projects, but that is not recommended as of now. So that is what we have for this computing units. The reason why we are discussing this particular point is we were discussing computational expensive part, right? So that's why I feel this is required. All right. So that is fine. What we'll do is now we will be taking a break, short break, and we'll be actually creating a model of by using random forest, right? Enough now. Let us discuss some practical scenarios. Even I am not. I mean, it's boring for me as well to discuss the theoretical part. Let us have some discussion on practical part, right? So what I'll do is I'll be using, let's create day 28. Yeah, today is 11th Jan 2025, and we are understanding entire random forest. I think we can wind up random forest in today's session, so that is a good part for us, right? And I'll just give you guys one data set which you guys already have, even though I'll just provide it over here. This one, hard disease prediction. And very first point that we have discussed in the last session itself, that random forest is always a better model than decision tree. You try to use random forest on any data set out there, any data set, 95% of the time you guys will be getting higher accuracy, right? So that's why it is considered as one of the good to go model directly without having a look at any data, like what is your data types, and without having um uh, in-depth notion of your data, right? People in the industry, we directly follow random forest. Let's apply random forest on this. So it's kind of favorite algorithm, you can say, for the people in the industry, right? Perfect. All right. Let us have a break now. It's 11, sorry, not 11, 10:33. Let's have a break for 10 minutes, 10:45, right? And what we have to do is after the break, we are actually going to perform um, your random forest on this data, right? So it is going to be fun. Chalo, let's have a break now. All right. Hi, everyone. So let us start working on this problem statement. Everybody knows what is our problem statement over here, right? We have to predict whether person has heart disease or not, right? So let us go. I think we have performed this thing. Yes, we have performed this thing in the last session itself. So let us take another data set, not the same one. Let us take another data set and let's use random forest in that data set, right? So that particular data set, I'll just upload it over here. It is churn data, CS. Again, very interesting thing. I was thinking to give this part as an assignment, but anyway, let's do that here only in class itself, right? Okay. So what this is all about? Churn data CSV, open, delete file as of now. Yeah. So it's a telecom churn case study, which is nothing but we have 21 predictor variable. We have 21 predictor variables and we need to predict whether a particular customer will switch to another telecom provider or not, right? In telecom terminology, this is referred to as churning and not churning respectively, right? So my step number one would be same, importing and merging the data. So I think not only one data, will require three data sets. So I'll just upload that quickly over here. We are going to use customer data. So that is already here. And we are going to use internet data. Is over here. Is this thing done, guys, or not done? I think this is also we have completed. I remember this. Can you guys quickly confirm, everyone? Done, right? Yeah, yeah. Okay. So we have left with nothing then. Okay, let me take another. Let me search. Just give me a minute. We can have basic uh, random forest model. It's already done, I remember. Just a minute. Random forest is something which, okay, I think we have done this in the random forest model itself. Here, right here, in this thing, right? Hyperparameter tuning, decision trees, multiple linear regression. Okay, not an issue. Let us focus on then theoretical part. Let's go back to where we belongs to, right? Let us do that. So what we have is now, what do we have is okay. You guys will be having one question that how to implement random forest. Let's do that. Chalo. Let's do it on hard disk data only. Here, I'll just remove this, kind of quickly import and run the data. Yeah. So we'll not be using decision tree. We'll directly be using random forest, and I'll show you a quick demonstration of how random forest is performed. So we are importing pandas as PD, numpy as np, import matplotlib.pld as this, cmon as this. Then we are going to read the CSV file and putting it into df object, right? So df is equals to pd.read underscore CSV heart, this one. So I can copy this path. I'm going to paste it over here. And as this is random forest, we'll not be going to perform outlier treatment and necessary thing. We'll be directly putting our variable into x and y. That is in x, capital X equals to df dot drop. I'm going to drop heart disease and putting response variable y is equals to df of heart disease, right? Then from sklearn dot model underscore selection, I'm going to import train test split, then x underscore train, x underscore test, y underscore train, y underscore test is equals to train underscore test underscore split, capital X comma y comma train underscore size is equals to 0.3, sorry, 7, and random state will pass it as any random state. Let's take it as 42, right? Then it's our time to perform random forest model directly. So we'll be using random forest model from sklearn dot ensemble. We're going to import random forest classifier, right? Now it's time to go for model building part. We have RF is equals to random forest classifier random underscore state is equals to 42. Our n underscore estimator is equals to 10. Our max underscore depth is equals to 3. And we are going to fit this on x underscore train, comma y underscore train. Random forest classifier and underscore estimators. and rf.fit x underscore train on this thing. So what we'll now do is we'll be actually creating estimator, selecting, we are selecting 10 estimators, right? So I'm selecting first estimator out of that, and it is in random forest. How many models do we have? We have 10 decision trees. So first is my decision tree classifier, in which I have max depth is equals to 3, maximum feature is equals to this, and random state is equals to this. What do you mean by estimator? Means you are going to use 10 different decision trees in your random forest. We have 10 different decision trees in your random forest classifier, right? Now we are going to just create one tree. Sample tree is equals to rf dot estimators underscore 4, and we are going to visualize the data. So okay, we will create one, we'll take the evaluate model function which we have created in the last session itself. If you guys remember, in this thing, yeah, we have created evaluate model function, right? So the same function we will create over here. Simple. We'll create over here, right? From and we'll use our this function evaluate model to calculate the accuracy of random forest model. So that is my RF, right? And it is going to be accuracy score is not defined. Okay, we need to import that. So we'll just write down from a scalar dot metrics import accuracy underscore score, and we'll be dealing with this. We'll dealing with this. Now it's again throws an error called as confusion matrix. Again, we will import confusion matrix. Try to use that. Now it is coming, right? So the accuracy for random forest is 0.74, and for earlier model, if you guys are using decision tree, your accuracy is 0.0. It was less, right? It was 0.60, so it was less. Now it is 0.74 and 0.61, so it is increasing. And again, you can perform hyperparameter tuning. That is not a difficult part for you as of now. So we'll just write down grid search for hyperparameter tuning, right? So we will be actually creating grid. So I left this part with you as part of your homework. Nothing special. You can have a look at the last session wherein we have done the hyperparameter tuning, right? You can create your hyperparameter tuning like this, and just create a parameters params grid equals to this, and in that you're going to add max depth equals to 1 comma 2 comma 5 comma 10 comma 20 comma minimum samples leaf is 5, 10, 20, 50, 100. And you have max features is equals to 2, 3, 4, comma n underscore estimators is equals to 10, 20, 10, 30, 50, 100, 200, something like that, right? And you guys will be using grid search CV now, and I'll left this part with you as part of your homework, right? Perfect. So now let us discuss this scenario where you can find feature importance using random forest model. What do you mean by that? Let us discuss this. Feature importance means in your data or from your data, from your data, from your data, let's say, let's take this data, the same problem statement on which we were working on, right? You have age, sex, blood pressure, cholesterol, and heart disease as part of your column in your data. So before actually building a random forest model, you can get an idea about the importance of feature variable, importance of the feature. For an example, which feature is important out of this, all the features out there? Which is important feature for you, right? You can get an idea about that. How? We have random forest for that. Similarly, we have seen in your decision tree also we have discussed this, right? How to understand the feature importance. Here also, your random forest will also give you an importance of features before actually building the model. So for that, the notion is random forest uses multiple trees, right? And it reduces variance, and it allow for more exploration. It allows for more exploration of feature combinations, right? So wouldn't it be great if you could use random forest for feature importance? So the importance of features in random forest, sometimes called as Gini importance, or mean decrease in node impurity. And it is weighted by probability of reaching that node, which is approximated by proportion of sample. So basically, let's not go into much depth of this. What you do is you calculate Gini importance, right? We have discussed that. And Gini importance, Gini impurity will tell us if you guys are doing splitting based on, let's say, BP column. Let's say the decrease in entropy, that is your Gini impurity, that is your information gain. You are getting it as, let's say, 0.5. And if you are doing splitting on cholesterol, let's say, if you are doing splitting based on BP column and you're performing decision trees, right? The information gain, the change in the entropy is 0.5. Now you have taken another feature, let's say cholesterol, right? And you obviously know that cholesterol, if you do splitting, the cholesterol is the good predictor for heart disease, right? So it is 0.7, decrease in the information gain is 0.7. So from this gene impurity itself, you get an idea about which variable is important for you, which variable is least important, right? So for each variable, we calculate the gene impurity. Simple. And that's what the idea is. Yes or no? Is it clear, guys, how we get feature importance from random forest? Right? Now, last but not the least, we'll discuss one point, and then we will be actually summarizing the random forest model. So let us go to official documentation of random forest. Let us now go to official documentation of random forest. Let us now go to official documentation of random forest, and let's try to understand each and every parameter out there. Like, what is n estimators? What is effect of max depth? What will be your effect of minimum sample lift? What will be your effect of max features, right? So the hyperparameters that we have in random forest, and effect of the hyperparameters, we'll summarize this as below. So we'll write on the effect of maximum features. So you learn that there's an optimal value. There's an optimal value of max features, that is very low values. The component trees are too simple to learn about anything useful, while at extremely high values, that is the component trees become similar to each other. So this is maximum feature, means it's an optimal value of maximum feature. That is, it should be if the values are too low, if the values is too low, it says that component trees are too simple. Let's say maximum features in your decision trees is tree is 3. So only 3 features will be there. That's all. It will be very simple. And if the values are extreme high, it becomes little bit complex, right? So that's what the idea is. Then we have n underscore estimators. What does it say is, when you observe the plot of n estimators and training and testing the accuracies, you'll see that uh, if you increase the n estimators, the accuracies of both the training and test sets gradually increase, right? And more importantly, the model does not overfit even when it is even if its complexity increases. So more importantly, your model will not overfit, meaning that if you increase n estimator, let's say n estimator is 5, if you increase to 10, 15, 20, your model will become your model complexity will increase, right? But on the other hand, you'll see a trend in increasing the accuracy of both training and testing accuracy, right? So more importantly, model will not overfit, even when its complexity is increasing, right? So this is an important benefit of random forest. That's an important benefit of random forest. Now you can increase the number of trees as much as you want, you like, without worrying about overfitting, right? You can increase the number of trees as much as you like without worrying about overfitting problem, right? And also you saw, since there were a lot of models to fit, the time taken was quite high, right? If you are increasing an estimator, obviously time will be high. Time will be high, right? So if you want to gain better understanding of time taken by to build random forest, you can minimize that. And so it should be optimized. Not necessarily you should add as high as possible an estimator. That should not be the case. You should be balancing, you should maintain balance between your time as well as accuracy, right? So that's what it is. That's what we have. So let us summarize this, whatever we have discussed till now. We have understood the concept of bagging. We have understood the concept of random forest, right? We have seen what do you mean by ensemble. We have seen what is diversity and acceptability, right? We have seen example for that, how to achieve diversity. We have discussed this. And how do you improve overall performance of the model? We have discussed that. We have seen some examples like this, very simple. And we have built a random forest model, right? So that's what it is. I think we have covered 90% of the syllabus in machine learning. Only 10% syllabus is left for us, which is nothing but your um, regularization. I'll write down over here. Tomorrow, or most probably the next week itself, will be winding up machine learning and we'll be starting deep learning part. So in the next session, we'll just see what is left for us. It is regularization. Then we have unsupervised as well, right? So hardly. Okay. Unsupervised machine learning K means PCA, hierarchical clustering. And then last but not the least, we have XGBoost. So boosting is remaining. Boosting. In that we have XGBoost, we have GBoost, and we have AdaBoost. We can finish this thing in 1 to 1.5 hours. That's not big deal. This is something which will require entire session, I suppose. Yeah. And regularization will also require 1 to 1.5 hours. So 3, and 1 session. So 2 sessions will be actually will need to finish this entire thing, what is left with us. So we still have half an hour. We'll be actually uh, going with the simple part. Let's go with the simple part now. Let's discuss unsupervised, right? In today's session. All right. So I'll just put a heading as unsupervised machine learning. Just kind of refresher for you. It's very simple. Does not require any technical expertise. Very, very simple part. Unsupervised machine learning. Right? Chalo. Anybody have any questions till now? You can ask. Anybody have any questions till now? Yes, guys. Do you guys have any questions? Did we completed all the classification? I think you mean to I mean, what you want to ask is, do we complete, is it completed this part supervised, right? Because classification comes under supervised, right? In supervised, you have classification as well as regression. So random forest can also be used for regression, right? It's not only for classification. It also can be used for regression. Decision trees can also be used for regression, right? So we were not actually dealing with classification. We were dealing with supervised machine learning approach. In supervised, we are left with these three models that we'll be discussing in tomorrow's session, because that requires some technical expertise. And having said that, you guys are already done with most of the theoretical part for today's session. So we'll not be actually dealing with that. Instead of that, we'll be actually going with the very simple part, that is clustering approach, that is unsupervised machine learning, right? Yes. All right. So I suppose you don't have any questions. Let's have a short break of 7 minutes. Let's have your coffee or tea, whatever you want, and we'll be starting the session at exactly 11:27, and we'll be understanding clustering. Let's finish this clustering in today's session itself, right? So let's have a break. All right, so let us discuss the clustering approach. Let us discuss the clustering approach. Now, in this thing, first of all, this is unsupervised learning, right? This is unsupervised learning module. In the last module, we have seen supervised learning, in which we have seen regression and classification, right? These techniques, uh, the regression and classification, these techniques use a training set to make the algorithm learn and then apply what it learned to new and unseen data points, right? So for an example, uh, what do you mean by supervised? Very first thing, supervised means you have an idea about the target variable. You know what we are going to predict, right? What is unsupervised? You don't have any labeled data, meaning that you don't have any idea about the target variable. The target variable. You don't have any idea about the target variable. Simple, right? So we don't have a data which will be labeled. Basically, label means you will not be having any, let's say, anything like you need to predict price of a car. You need to predict whether a person has heart disease or not. That will not be a problem statement. So what do we do then? How do we solve what will be your approach for that? What we do is we try to find the patterns based on similarities. Very simple, similarities in the data. What do you mean by similarities? Let's say, do you remember I've given you guys, I have given some example for this, for unsupervised machine learning. Let's say you are working in a as a data scientist in a mall, let's say Geo Instamart, let's say, right? Geo Instamart. So what we have seen is uh, we wanted to create strategies for those customers who are highly capable to spend in our mall, but they're not spending, right? So we have uh, annual income for the customers, right? Somehow we have managed to take this data in which we have annual income and the spending capacity or spending score out of 100. Spending score out of 100. So 1, 2, 3. Suppose these 3 data points are here, these 3 data points are here, and these 3 data points are here, right? You could have this data points as well. You could have this data points as well, right? So what do we do is we kind of cluster this data point. So similar data points, the data point which has high similarity will be part of a single group, a single cluster, right? Can you make cluster like this? Let's say this and this data point. Can you make cluster like this? No. Why? Because these are not similar, right? These are not similar data points. Similarly, you cannot create a cluster. You cannot create cluster like this and cluster. This is another cluster. Will that be case? Certainly not, right? Clusters we can form based on the similarities. Like these data points are similar, we are creating cluster for that. These data points are similar, we are creating clusters for that. These are similar, we are creating clusters for that. These are similar, so we are creating clusters for that. and these are also similar. So we are creating clusters for that, right? So your task is to target which customer? Your task is to target this customer where their annual income is very high. Let's say 1 to 2 lakh. This is 50,000. Let's say this is 20,000 per month, right? Or it's annual income, right? Anyway, let's consider this as the monthly income. And spending score, like this customer has 90 spending score. They're spending very good. This customer has in between 50, and this customer has very less spending score. So even though this this customer, they have high annual income, let's say 1 to 2 lakh per month, but they are not spending much on your mall, in your mall, right? But they have capacity, right? They have potential to spend huge amount of money, but they're not spending. So indirectly, what will happen if we target this customer? Let's say we kind of strategize this customers and create a platinum card, or buy one get one offers, or more attractive offers. If you buy for 10,000, you guys will get flat 2,000 off, something like that. Yes or no? So that kind of thing comes under your unsupervised machine learning, right? So we learn two most commonly used uh, types of clusterings here. One will be your K-means clustering, and another will be your hierarchical clustering. I'll kind of give you guys an example of those two clusterings as well, right? So please allow me to go little fast now. Now what we'll do is we will see some practical implications of clusterings, right? Practical applications of clustering, right? So let us increase the font for this one. All right, first one is customer insight. Customer insight. Say a retail chain with so many stores across locations wants to manage stores at best and increase their sales and performance, right? Then you can have marketing, another powerful segment. It will help us to understand market segmentation, help in market segmentation, positioning, and identify test markets for new product development. And then we have social media with us. In the area of social networking and social media, cluster analysis helps us to identify similar communities. Within larger group, right? Then you can have medical segment where it helps us to understand the field like human genetics, human genetic clustering, or kind of sequencing your data into gene families. And we are going to build groups of genes and clustering of organisms uh, at species, right? Different species will be consisting of different clusters like that, right? So there can be n number of things, and trust me, guys, this is going to be very helpful for you in your real case scenario as well. You can find n number of applications related to that, right? N number of applications. So I'll tell you one scenario, practical examples. I'll just kind of read it, the example. Suppose you have an online retail, just like your Amazon or Walmart, right? Basically, Walmart is not online, but still we can consider that. Customer segmentation for targeted marketing is one of the most important applications of clustering algorithm. Let's say you are working as a manager in an online store or manager of the online store, right? You would want to group the customers into different clusters so that you can make a customized marketing campaign. Customized marketing campaign um, for each of the group. You do not have any label in mind, such as good customer or bad customer. You don't have that. You want to just look at the patterns in customer data that is provided for you, right? And then try to find the segment, try to find segments. And this is where clustering techniques can help you out with segmenting customers. Like clustering techniques use this raw data, which is provided to you, to form clusters, to form clusters based on common factors among various data points. And this is exactly what else will also be done in segmentation, where various people or products will be grouped together on the basis of similarities and difference between them, right? As a manager, you would have to decide what the important business criteria are on which you would want to segregate the customer. So, as a manager, you would have to decide what the important business criteria are on which you would want to segregate the customers, right? So you would need a method or an algorithm that itself decides this, right? So you don't have to spend any energy on that. You would need a method or algorithm that itself decides which customer to group based on this criteria. Yes or no? It sounds interesting, right? Well, that's the beauty of unsupervised learning, especially your clustering. But before we conclude this thing, uh, we can just have discussion on uh, what happens in the industry, right? So there are three types of scenario, three types of segmentation. You can read about this thing. We'll not be discussing this specifically. Three types of segments, uh, customer segmentation, basically, not segment. We have psychographic, demographic, and attitude. So basically, behavioral is the one thing where we is based on the actual pattern displayed by the consumer, right? Attitudinal means it is based on the belief or the intent of people, sorry, which may not translate into similar actions. And we have demographic, which is nothing but it groups based on certain criteria like age, gender, income, and occupation. So you can consider these three: psychographic, behavioral, and demographic. There are three types of customer segmentation, and if you just go on exploring this thing anywhere on internet, you'll find some articles, some videos for that. It will help you out to understand how the clustering works, right? So it's very simple. You can go and
Hi, this is my girlfriend.
anything is fine. To understand this in more detailed fashion, right? Like you can take any sector out there, any sector will be having customers. So what will be their segmentation? How we can decide the segmentation? So we have these three types, right? I will share some business case studies. Just give me uh there's one website. Yeah, this is what I'm talking about. You can read this thing, very interesting article, to just get an idea about the interesting use cases for the k-means algorithm. So you'll get everything related to this. Anyway, we are going to learn this thing. We have document classification, delivery store optimization, uh, identifying crime localities, customer segmentation, fantasy leak statistical analysis, insurance fraud detection, ride share data analysis, cyber profiling, criminals, call record detail analysis, automatic clustering of IT alerts, and much more than that, right? So you can read about this to get a better understanding of how clustering will help you out in real world scenario, right? All right. So that's what we have. I think we can go to the next part where we'll be actually dealing with k-means clustering, to be more specific. K-means clustering. So the idea here is to use KNN in unsupervised machine learning, right? KNN means what we used to do? We used to find distance between the data points, right? Here also we'll find distance between the data points, but in unsupervised manner. So it's kind of same like your KNN only. So in this thing, what we'll learn is we'll learn about the steps in the k-means algorithm. We'll be actually having a look at how to graphically visualize the steps of k-means algorithm. It's just like this thing only, guys. See, what do we do is we plot data on x and y axis, right? Suppose this is your data. We put that into different clusters like this. We put that into different clusters like this, right? So how do you find clusters? These are the steps, right? You don't need to do this thing manually. An algorithm will help you out to do that, but we are trying to understand the what happens in the back end of your algorithm, right? So how to graphically visualize the steps of K-means algorithm, and then we are going to see practical considerations while using the K-means algorithm. How to graphically visualize this steps in the k-means algorithm, practical consideration while using the k-means algorithm. Simple. So what do we do is we kind of plot the data. Let's say suppose we have only 2 data points, or let's say 4 data points. So what we'll do is we'll find the distance between these data points. So let's take reference as this data point. The find distance between this, find distance between this, find distance between this, right? So in your school days, you have seen the Euclidean distance formula, right? Everybody knows that. It is under root of x2 minus x1 square plus y2 minus y1 square, right? So that is something which we use over here, right? So suppose you have 2 data points or you have data points, this one, you kind of convert that into clusters and then find the Euclidean distance. To find Euclidean distance, we have this formula. So suppose you guys have this point and this point. This point has coordinate x1, y1. This has coordinate x2, y2, right? You'll find distance as x2 minus x1 square plus y2 minus y1 square. Yes or no? So that's the thing we use over here, that is known as Euclidean distance, to calculate the distance between two data points. So in the previous segment as well in KNN, you guys got an idea about Euclidean distance, right? It groups, basically you find the distance between the data points by using Euclidean distance. The distance measure that we use in K-means is called as Euclidean distance, and I have already explained uh, how to calculate this distance between the two data point, right? So basically, can you guys answer this question? So the observations, the data points, which are closer to, closer or more similar to each other, and the observations or data points which are farther or less similar to each other would have uh, you have to comment this thing, the Euclidean distance, about the Euclidean distance, whether it is high or low. So for which case it is high, for which case it is low, right? Data points which are similar to each other will be having dash dash distance, and the data point which are farther will be having high or low Euclidean distance. What do you think, guys? For first thing, what do you think? And for second, what do you think? First is low. Very good. Second one is high. Simple. So this is what the intuition is for your K-means, right? If you guys have understood this concept, it means that you have understood K-means. If you guys have understood this point, it simply means that you have understood the K-means model. And what is that? It is the data point which are closer to each other, the data point which are closer to each other will be having less Euclidean distance, means they are similar to each other, and the data point which are farther to each other will be having what? Higher distance, higher Euclidean distance. End of the K-means clustering algorithm, right? So once you have computed the Euclidean distance, step number one, what do you do is you compute the Euclidean distance of the data points. Now, next step is pretty straightforward for the clustering algorithm. All it has to do is to compute these distances and then find out which observation or points have a low Euclidean distance. So which observation or point has low Euclidean distance, right? That is, they are closer to each other, and then cluster them together. Suppose they are closer to each other, then we cluster them, right? Perfect. Now there's another term which is known as uh, centroid. We'll be discussing that. Centroid. Let us discuss that. There's another term which is called as centroid. Let's discuss that. So next concept that is crucial for understanding how clustering generally works is the idea of centroids. If you remember your high school geometry, centroids are essentially the center points of triangles, right? So centroids are generally center points. Similarly, in the case of clustering, centroids are the center points of the clusters that are being formed, right? Now, before going to the formula part, here's an intention for the need of a centroid. Imagine you have following clusters of the marks of a group of students uh, in mathematics, in biology, and someone asks you to explain them, right? So from a glance, you can easily interpret the flow four clusters that is being formed over here. So I'll just kind of draw these clusters: cluster number one, cluster number two, cluster number three, and cluster number four here. On the x-axis, I have marks in mathematics marks, and on the y-axis, we are having marks in biology, marks in biology, right? And these are my data points. Let's say 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, right? So this is C1. Let's call it as C2, C3, and C4. So the four clusters that are being formed are as follows. Cluster one is students who have scored high marks in bio, but poor marks in mathematics. Cluster two is students who have scored average marks in bio and mathematics. Cluster three is high marks in bio, high marks in mathematics. Cluster four is low marks in bio, high marks in mathematics. Yes or no? Now, the above representation is fine and correct. But what is missing is, let me take this up. Let me paste it over here itself. And let me just minimize the size. Right? Okay. Chalo. So C1 is, what is that? High marks. Or instead of that, let's do one thing. Let us write on bio, maths. Marks is high, marks is low. We have cluster number two is average, average. We have cluster number three, high in both. And we have cluster number four, that is high in maths, but sorry, low in bio and high in maths, right? But the above representation is fine and correct, but what is missing one crucial information, that is the numerical order. For example, when you want to compare two clusters, say cluster number one and cluster number two, how do you compare this, right? By how much, can you say by how much marks on average do the students from cluster number one outperform or underperform the cluster number two? We don't have any idea about that, right? So, uh, students in a particular subject just by taking at the look at the above visualization alone. Is it by 10 marks? Is it by 5 marks? The quantitative representation is not there, right? And this is where the concept of centroids comes into the picture, comes in handy, right? So let us discuss this centroid concept in some other, not other, in tomorrow's session, right? So before that, I'll just actually kind of create a data and we'll stop here for the day. Centroid thing which we are interested to find. So let me take a data. Okay, let's create a table. We have an observation that is A, B, C, and D, right? We have height for this person, and we have weight for this person, and we have age for this person. So 175, 165, 183, 172. Weight is 83, 74, 98, 8080. Age is 22, 25, 24, 24, right? And I'm going to now we are going to see how cluster centroids are calculated. Centroids values are computed. How it is computed, right? So what is cluster centers? First of all, centroids are essentially the clusters centers of a group of observation group of observation that help us in summarizing the cluster's properties, right? Thus, as you saw in the video, the centroid value in the case of clustering is essentially the mean of all observations that belongs to a particular cluster, right? So mean of all the observation, 175 plus 83 plus 22. If you take average of this, it will be centroid, that is 93.3. No, sorry, not this. My bad. For height, right? For height. So it should be average of height. Average of height. The centroid is calculated by computing the mean of each and every column, that is dimension that you have, and then ordering them in the same way, like this. Average, each and every column. Again, average, each and every column out there, right? So the centroid of the above group of observations are 173.75, 83.75, and 23.75, right? You can do this thing, like you can plot this. So 3 dimensions will be there: height, age, and weight, and you'll try to find the centroid. So that's what we have for the centroid concept. Again, in the next session, that is tomorrow, we are going to discuss this. Don't worry about that, right? So we'll just kind of summarize this. So you guys go through this. If you have any questions, you can ask. We'll stop here for the day. Today, we have completed the random forest and we have started the k-means algorithm. Now let us discuss the questions. Can I take my reference data point or finding Euclidean distance randomly, or There are some criteria to choose them. We have not discussed that yet. That comes under your steps of uh, K-means clustering, right? See, while starting the K-means clustering, we have seen this agenda, right? This is going to be your agenda. So we have not started it yet, right? We still have not started, not touched this topic. So steps in K-means clustering, whenever we are going to discuss that, anyway, that is going to be your next part. Let me write down over here. Steps in K-means clustering. Steps in K-means clustering, right? Let me take that. Let me write down over here. That is going to be my next part. So don't worry about that. Here you'll understand how we perform with this thing, right? How do we find the centroid? It's kind of very interesting. So anybody else? Do you have any questions? Yes, guys. Abdul, Arvind, Arivoli, Arun, Binu, Chandramohan, Darshini, Gopi. Then we have Kannan, Madhu, Maulya, Murali, Prasita, Sharmila, Thammi, Varun, Karthik, and Thangamani. Yes, guys. Do you have any questions?
No, Vipul.
Well, all right then. If you don't have any question, we'll stop here for the day. We'll continue with the next part in the tomorrow's session. So thank you everyone. Happy learning. Bye.